So what I'm going to do today, I'm going to do like one more example on like dependent sources, and then I'm going to move on to Delta-Wye transformation, which is like another tool for us that we can add it to the bag of tools that we got. Okay. So the very first example I want to do is a small signal model for a MOSFET. Probably none of those words actually make any sense to you, which is totally fine. I'm going to just like give you like a quick review of like what it is, and then I'm going to give you the circuit. Even though like those words might not make sense to you, the circuit should make sense to you. Well, what are the main components of like your CPU or any logic gates that we have as a MOSFET, which is a transistor, right? And if you look at like transistors, transistors are highly nonlinear. Okay. To be able to analyze the circuits with transistors in it, what we have to do is we have to like use formulas associated with them. But sometimes what we're interested in is that if I change my input a little bit, how would it affect the output, right? Usually whenever we're talking about like a little bit, we're talking about like Taylor expansion, right? So if I have like this formula for my input, if I write the Taylor expansion for it, how would that little change that the Taylor expansion gives me would affect my output? It turns out to analyze a circuit to see like how the output is impacted by the little change in my input, I have to have like an equivalent circuit to be able to analyze it. That equivalent circuit is called a small signal model, right? A MOSFET, like I said, is just a transistor, right? What we're interested in is that if I have like a common source MOSFET or a common source like amplifier, how would output change if I change a little bit like my input? So to be able to do that, I have to use like dependent sources to model the circuit. And the circuit that I have is as follows. This is called MOSFET common source amplifier. The circuit is very easy. The circuit is a voltage source that changes with time. It's followed by a resistance, R1, another resistance, R2. And then we have a dependent current source where its value is being controlled by a voltage, VG of t, which is voltage across this R2. Right? And it's followed by 3 more resistors, R3, R4, R5. And what we're interested in is voltage across this R5. And like I said, whenever we're talking about like these things, we're talking about gain. How would like a little bit of change and input would impact my output? So basically what I'm also interested in is a gain, which is the ratio of output to the input. Right? Which is something that I want to find. Let's just assume VI or V input. Just write it as V input. Let's just say V input, R1, R2, R3, R4, and R5, they're all given to us. Okay? Assume we know R1, R2, R3, R4, R5, GM, and V N of t. For example, let's just assume R1 is 100 ohms, R2 is 1 kilo ohms, R3 is 50 kilo ohms, R4 and R5 are 10 kilo ohms, and let's just say GM is 0.04. right? So these are all given to us. That's just an example, right? So the question asking me, I have that circuit with like those given parameters. What is V out? And now you know V out. What is the ratio of V out to V in? Okay. So this is a circuit that we're familiar with. We know how to solve like circuits that look like this, right? What is the first thing we notice in this circuit? The very, very first thing that we notice is that R3, R4, and R5, they're in parallel, right? Why? Why are they in parallel? They have like the same head and tail, right? What else do we know about R2, R3, R4, and R5? We know since they're in parallel, if voltage across R5 is V out, voltage across R3 and R4 must be V out too. And also, if I replace it by its equivalent, still voltage across the equivalent would be V out. Right? So let's do that. Let's just combine these with like its equivalent. So if I do that, let's just call it R equivalent. R equivalent is R3 in parallel with R4 in parallel with R5. Right? So let me redraw the circuit. Given this, I can redraw the circuit. I have V input of t, R1, R2, voltage across R2 is VG of t. I have this dependent source with value GM VG of t. And then I have this R equivalent, which is this guy, right? And I also know voltage across this V equivalent is V out, right? We know it because R3, R4, and R5, they're in parallel. Okay? We have a circuit with a dependent source. If you guys recall, what we said about dependent sources was we always treat him like a regular independent source, but since its value depends on something else in the circuit, we always have to obtain that value somehow in the circuit and then plug it into the formulas that we have. If you look at here, this is a dependent current source, which is being controlled by voltage in the circuit, which is voltage across that R2. So I got to be able to find that VG of t. Well, let me write a KVL here. If I write a KVL here, what do I have? I have R1 times IT plus R2 times IT. That should be V in of t, right? Because what KVL was telling us was if I loop around a closed loop and I add up all the voltages, that should add up to 0. And that's exactly like what this is, right? I know R1 and R2, so I can factor out this IT, and I can compute IT as V input t divided by R1 plus R2. Again, there was a simpler way of doing it. R1 and R2, they're in series. Voltage across it is Vn, you have Ohm's law. But I wrote KVL. Let's call this thing equation 1. Given this IT, do I know VGT? Do I know voltage across R2? I do. I have Ohm's law. So I have R2 times I of t. I'm going to plug in equation 1 here. So I have R2 divided by R1 plus R2 times Vn of t. Right? That is equation 2. Again, this equation should be familiar to us because that's a voltage divider. Right? Look at this circuit. I am claiming I know exactly what V out is. Why? What is V out in general? V out is a voltage across the resistance. How do we find it? Ohm's law. So if I know the value of the resistance, and if I know the current through it, I know voltage across it. I'm claiming in this circuit, we know exactly what's happening. I know R equal, well, that's the formula that we had up here, right? So I know R equivalent. What I'm claiming is that I know current through R equivalent as well. If it's something funny, if there's a question, you can ask me. So I know exactly like current through R equivalent. What is it? Look, I have that current source that dictates exactly like what value of the current I should have through R equivalent. Right? So what is the current through it then, given this polarity? Is it GM VGT or negative GM VGT? It's negative, right? So I have R equivalent times minus GM VGT. And this is again based on Ohm's law. Right? If I look at this equation, I don't know VGT, but I already computed it. That's my equation 2. I can plug it in here. So that's the same as R equivalent times minus GM times VGT, which is this guy. It is R2 divided by R1 plus R2 times Vn of t. Now, if I look at this equation, everything is known to me. Right? What is the gain? What is V out over V in? Well, it's like very simple, right? I already know like this relationship. I just need to bring this thing down there, right? So I need to bring this one down here. So that would be minus GM R equivalent R2 divided by R1 plus R2. Right? So the whole idea here was that I know KVL and KCL, I know the parallel connection, I know the relationships in parallel connection. I can use all those things, simplify the circuit to a circuit that's much easier to work with, right? And then I use Ohm's law, right? As soon as I find V out, then finding gain is like very simple, right? Because it's just division, right? Is this clear? Are you guys with me? Does that make sense what's going on? Yes. You had a question? Okay. Clear to everybody? Yes. That's basically the gain. That's basically tells you like if your input changes with like a little bit, this is the amount that your output would change, right? And if you go back to the definition of like this circuit, this is a common source amplifier. And this is the rate, this is the gain that it amplifies your input, right?
Why do we use 3 resistors on the common source amplifier?
Oh, there are like implementation things. Yeah, that's basically like how they're modeled. And if you look at like the values for them, the values are like different, right? So it's just the way it's implemented. To be able to like answer that question, I got to go over like transistors. So just take it from me, that's just the implementation thing. But to give you like a very quick idea is that like when you're writing the Taylor expansion of it, the Taylor expansion would give you those 3 elements, right? Because you have to like find like the partial derivative, and the partial derivatives would give you like all those elements. But again, it's not a concern. That's the way it turns out to be. Any question about this circuit, the way that we solved it? We good? So now we got this out of the way. Let's talk about something else. So far what we learned was we learned about KVL and KCL. And as a result of that, we learned about voltage divider and current divider, right? We talked about like connections. We said there are 3 types of like connections in general. We have series connection, which means like the resistors are back to back, and whatever current that's going through one of them should go through all of them, and it remains the same. And if I replace it by the equivalent, the current through it is the same as the current through each resistance. We talked about parallel connection. We said resistors are in parallel if they're sharing the exact same head and tails. And what we knew about it was voltage across each resistance is the same. And if I replace the whole thing by its equivalent, voltage across the equivalent was the same as like voltage across each resistance. The third one was it's neither of them, right? If it's neither of them, basically we're stuck, right? So the way that we can solve the problem is just using like the KVL and KCL and all those things. There are specific cases that people like use that a lot. Circuits basically use like those specific cases that engineers were like, okay, if I have like this specific case, can I make it like easier for me to analyze the circuit? For instance, if I have a circuit that looks like this, let's just say I have this, R2, R3, and R4, and R5. If I look at this circuit, what's the relationship between R1 and R2? Nothing. They're not in parallel because there is R3 in between. So they're not sharing the exact same head and tail. So they're not parallel. Are they in series? No, because of like this guy up here, the current here actually splits between these two. So the current is not exactly the same. I can say the same thing about like R4 and R5. There is no relationship between them. But it would have been very nice if I could replace this triangle up here with a circuit that looked like this. Right? It would have been like much, much easier. Because as soon as I replace that triangle with this upside down Y, now I know these 2 resistors, this one and this one, they're in series. This one and this one, they're in series. The result, these 2 and these 2, are in parallel, and then the whole thing is in series. So it would have been very nice if I could just replace that whole triangle thing with a Y, with this upside down Y circuit. So the question is, can I do that? Can I basically, so this is my goal. If I have these three resistors, let's just say this is between nodes A, B, and C, R1, R2, R3. Can I replace this delta with a circuit that looks like this? Again, between nodes A, B, and C. Let's just call this RA, RB, and RC. Such that the remaining of the circuit remains unchanged, and the external behavior of the circuit also remains unchanged. Basically, if I'm looking at I here, or like voltage across this, since this is not a part of this triangle, I want the voltage across them, for example, or current through them, to remain unchanged when I'm going from triangle to the upside down Y. So the goal is to have a replacement for this. So the question is, find RA, RB, RC such that the external behavior of circuit remains unchanged. And as I mentioned, since like this is not a part of like this triangle, if I want to find current through this, if I replace this triangle by this Y, this current should not change. So I have to obtain RA, RB, and RC such that this happens. Okay? Let's see if we can actually do that. But look at this guy. If we're able to do this, like I said, if we're able to do this, this makes our life like much easier, right? And because this is a very famous thing, this is called Delta-Wye transformation. Because this guy looks like a delta, this looks upside down Y, they call it like Delta-Wye transformation. So this is called Delta-Wye transformation. So now our question is, let's find RA, RB, or RC. Or vice versa. If I'm given RA, RB, and RC, I got to be able to go back to like R1, R2, and R3. They're equivalent. So if I have like the delta, I should be able to go to like Y. If I have Y, I should be able to go to delta. So let's see like how it works. Let me redraw this. Let's just say, again, this is A. This is R1. This is B. This is R3. This is R2. This is C. I want this to be the exact same as this guy. This is A, this is B, this is C. RA, RB, RC. Right? If they're equivalent, if I look at between nodes A and B over here, that should be the exact same as node A and B over here. Let's just call that R, A, and B. What is R, A, and B in the delta circuit? If I wanted to like find the equivalent there, what is it? That's basically that R1 in parallel with R2 and R3 in series. Right? Look, these two are in series. And since they're sharing the exact same head and tail with R1, they're in parallel. So I have R1 in parallel with R2 plus R3. And I know the formula for this thing. That's R1 times R2 plus R3 divided by R1 plus R2 plus R3. How about here? If I wanted to look at here, what do I have? If I look between like these two, since this is not connecting to anything, it's just somewhere else, these two things are in series. With the exact same logic, if I look at, for example, BC, R3 is in parallel with these two in series. So that's basically R3 times R1 plus R2 divided by R3 plus R1 plus R2. And if I look at it here, that would be RB plus RC. And similarly, if I look at CA, I have R2 in parallel with R1 plus R3, which I know that's R2 times R1 plus R3 divided by R2 plus R1 plus R3. And if I look at it over here, that should be RA plus RC. Depending on like which one of these is given to me, I have three equations, three unknowns. I can solve for whatever I want. Assuming like RA, RB, and RC are given. So this side is given. This is unknown. Three equations, three unknown, I can solve for. If R1, R2, R3 are known, then this side is known. I can find RA, RB, and RC. I make your life easier. I'll give you like the formula for it. I'll basically solve this thing, and I basically give you like the final formula. But if you forgot, this is how you can actually find it. So let's do this. So let me just make a quick note. Three equations, three unknown. We can solve for unknowns. Let's just say I'm given this guy. Let's just assume RA, RB, and RC are given. And what I'm assuming is basically I am given Y. I want to find delta. If I want to do this, it turns out R1 is RA, RB plus RB, RC plus RA, RC divided by RB. R2 is RA, RB, RB, RC, RA, RC divided by RC. R3 is RA, RB plus RA, RC plus RB, RC divided by RA. In a second, I'm going to tell you a trick to memorize this. But for now, these are like the formulas. What happens if RA is the exact same as RB, is the exact same as RC, and equals to RY? What is R delta? First of all, I know R1 is the same as R2, is the same as R3, and that should be R delta. But what is R delta in terms of RY? Again, just plug them in here, right? If you plug them in here, you have ry squared plus ry squared plus ry squared divided by ry. So it's 3 times ry. Right? So R delta is 3 times ry. It's just a special case. Okay, this is a special case. Let's just assume now we know R1, R2, and R3. Basically, I know the delta, and I want to find Y transformation. It turns out RA is R1, R2 divided by R1 plus R2 plus R3. RB is R1, R3 divided by R1 plus R2 plus R3. RC is R2, R3 divided by R1 plus R2 plus R3. And again, if we want to look at like the special case, let's just assume R1 as R2 as R3 equals R delta. We know RA must be the same as RB, must be the same as RC, and that's RY. What's the value for that? Again, you can plug them in there, right? So you have R delta squared divided by 3 R delta. So it's 1/3. Or you could just like cheat off of here, right? We already said like R delta is like 3 times RY. Therefore, RY is like 1/3 of R delta, right? So it's like 1/3 of R delta, right? These are rather complicated like formulas. I'm very bad at memorizing things. So let's just like see how we can memorize it. So let's just say I have this guy. I have, what was my notation here? R1, R2, R3. This was A, B, C. I replace this by a circuit that looks like this. We call this RA, RB, and RC. Right? A few points. If I look at the delta, how many nodes do I have? 3, right? A, B, and C. But as soon as I go from delta to Y, I'm creating one node in the middle, right? So as soon as I go from delta to Y, instead of having 3 nodes, I have 4 nodes. This specifically will come handy later on in this class when we're analyzing circuits in a more complicated like fashion. Keep that in mind. Let's just see how we can actually like memorize this thing. What do I have? It's right here. Let's just say I want to find R1. Well, on the numerator, it's all the possible combinations of like 2 resistors. So that's easy to remember. It's RA, RB, RB, RC, RA, RC. It's all possible combinations of 2 resistors. What's a little difficult is like whatever that goes on the denominator, because that's the only difference between like these 3, right? But look, if I want to know R1, is that like how I named them over here? Because if that's how I named them, then I made a mistake. Then this should be RC, sorry. This should be RB. And this should be RA. Right? Because whenever I'm writing for R1, R1 should like see RC. And that's what goes on the denominator. If I'm writing for C, basically R2, R2 seeing RB, so RB goes down. If I'm writing R3, R3 is seeing RA. Right? And that's how you memorize it. See, I'm already very bad at it. Right? But the way that you can remember is that like you got to look at R1 and see like what it sees. It sees RC. You look at like R3, it says RA. I look at R2, it sees like RB. Right? Going from here, from delta to y is like much easier because RA is between like these two. So it's R1, R2. So it's R1, R2 divided by the whole thing. RC here is R2, R3 divided by whole thing. It's R2, R3. RB is between R1 and R3. So it's R1, R3. Right? Any question? Any question? Yes. Sure. So let's do a quick example and see like how it works. Any question about like these formulas? These are just a bunch of like formulas. It's not very complicated, right? And anytime we're confused, we can always like go back to like those three main equations and solve for it, right? So let's do like a quick example and see like how things work. Example. Let's just say I have this 36 volts. I have a 6 ohms resistance here, another 6 ohms resistance. I have a 6 ohms resistance here, 3 ohms here, 3 ohms here, 6 ohms here, 6 ohms here, 3 ohms here, 3 ohms here. Okay? And the question is asking me what is I naught here. Okay? What can we do? Any idea? Well, if you look at this circuit, this is not exactly like the delta circuit, right? But we can make it delta. How? Look at these two. Do you agree these two are in series? So I can combine them. So I have 3 plus 3, which is a 6 ohms. Now what do I have? Now I have a delta. This is my node A, this is my node B, and this is my node C. Right? As a matter of fact, this is a special case. Right? This is the special case. All the resistors are 6 ohms. So I can replace that by its Y equivalent. What is RY? What's the relationship to R delta if they were all equivalent? They were all equal? It's 1/3 of that, right? So it's 1/3 R delta. In this case, R delta is 6. So it's 2 ohms, right? One thing I need to pay attention is that like to replace the delta by Y, I got to make sure that I'm using the right nodes. In this case, it wouldn't matter much because they all got the same number. But if they were different, then I have to like make sure A goes to A, B goes to B, C goes to C. Right? So over here, this part of the circuit remains unchanged. This is 36 volts. I have 6 ohms here, another 6 ohms here. This is A, this is B, this is C. Over here, it remains unchanged. So this is 6. Over here, it remains unchanged. This is 3. This is 3. Between A and B, well, it's going to be something like this, which is 2. another 2, another 2. Right? So this is my equivalent. What can I do now? What can I do now? Do you agree this 2, this 3, and this 3, they're all in series? Right? So the equivalent is 2 plus 3 plus 3, which is 8. How about these two? Aren't they in series? They're in series. So that would be 2 plus 6, 8 ohms. So if I redraw the circuit would look like this. Two. We have an 8. We have an 8. And that's it. Do you agree with me? Do you agree this circuit on the left is the same as the circuit on the right? Do you agree with me? I just combined. Do you agree these two are in parallel? So I can replace it by the equivalent one, right? 8 and 8, they're exactly the same, so the equivalent is half, right? What I'm claiming is that I know voltage across each of these 8s. How? Is this circuit familiar to us at all? What is this circuit? That's a voltage divider. That's a voltage divider that has one voltage source followed by 1, 2, 3, 4 resistors back to back. So if I want to find voltage across this 4 ohms resistance, what is the voltage across it? I know the voltage across is proportional to the value of that resistance divided by the whole thing. So voltage across this, let's just call it V1. V1 is 4 divided by 6 plus 2 plus 4 plus 6 times 36, which is 8 volts. Right? I know V1 is 8 volts, and V1 is voltage across the 4 ohms resistance, which is 8 and 8 in parallel. What is voltage across this 8? What is it? What is it? It's exactly 8. Why? Because these two are in parallel. If voltage across this 8 is also 8 volts, what is current through it? What is current through it? One. Why? Because we have Ohm's law. I know voltage across it. I know the value of the resistance. I know current through it. So that would be 8 divided by 8, which is 1 amps. And this is Ohm's law. Do you agree this I naught over here is exactly that I naught over there? Do you agree with me? Why? Because this I naught is current through this 8. And this 8 is this 2, 3, and 3 in series. And that's exactly the I naught that we were looking for. This was our I naught. Right? Remember, if I replace the delta by its equivalent, the external behavior would remain unchanged. Therefore, this I naught should remain unchanged if I go from delta to y. And it remains unchanged. Therefore, if I go from here to here, I naught is still 1. right? Any question about this? Any question? Yes. Mhm. Perfect. So what I assume is that like, if I have RA, RB, and RC, they're known to me, and they're exactly like the same. The values are basically like 5, 6, right? They're all the same. I'll call that RY, which is the common value, right? If that's given to me, if I wanted to find R1, R2, R3, which are the ones associated with my delta circuit, I call it R delta because they're all going to be the same, right? And the value is 3 times RY, which is that value up there, right? Same thing over here. If I'm given R1, R2, R3, which is my delta circuit, and I say like all of them are the same and the values are delta, right? 5, 6, 10, whatever, right? That's given to me. And you're asked to find RA, RB, RC, which is your RY associated with the Y circuit. It turns out the value of RY is 1/3 of the value of R1, R2, R3, which we called it R delta. No. Let's just say R1 is 5, R2 is 5, and R3 is 5. I called that 5 R delta, right? Over here, I have RA, RB, and RC, right? Let's just say RA is 5, RB is 5, RC is 5. I'll call that 5 RY, right? It's just the value of it, right? I could just forget about it and just write R3, for example, or R1 or R2 as 3 times RA or RB or RC. It's the same thing, right? But since they're like exactly the same, I gave it a name, RY. Any question? Any question? Again, I want to just go back to this one. What goes on the denominator here is what this R1 is seeing, right? In this case, this R1 is saying RC. This R2 is saying RB. This R3 is saying RA, right? And if I want to find, like, for example, this RC is located between these two. So the numerator is going to be this times this, right? Is that clear to everybody? Does that make sense what we're doing? So what we're going to do in like we're going to be doing on Friday, we're going to do a few more examples on Delta-Wye transformation, and then we're going to learn about like nodal analysis. All right, I'll see you guys Friday.